Hello everyone. So here we are again. So today's topic is nothing that much complicated, but in today's topics we are going to use a little bit of some properties of trigonometry that we learned in the last video. So if you want to know more about trigonometry, I just invite you to see our previous section about trigonometry. You will go like you're going to see many things in a different perspective, and that will help you a lot, I can assure you. So you will stop thinking that trigonometry is is something really difficult if you go through through these videos. Okay, that video about trigonometry is not still complete yet. Okay, but okay, what you have there is the consistency basic. Okay, consistency basic basis to you to grow up and to just increase your understanding about trigonometry. So today we are going to apply some of the knowledge from that class. Okay, so we are going to apply to this topic over here. So what is this topic actually? So this is all about the complex number. So first, before we just today we are going just to prove, okay, to prove this identity for the argument of this complex number. So we know that first, all complex numbers or any complex number is a number that can be written in this form. Okay, z is equal to I plus a plus ib. Okay, a plus ib, where this a over here is the real part of z. Okay, it's like the real part of z. Okay, and this b is the imaginary part of z. So this part here is the imaginary part, then this one is the real part of this imaginary number. So any number that you can write in this form can be considered as a imaginary number. I'm just giving you a hint on basis about this imaginary number. So suppose we want to represent this imaginary number in this in the plane, just to you to have a note. Here I know that will be the axis for the imaginary part of this imaginary number. Then here it will be the real axis for the real part of this imaginary number. It means that whatever a that you got here, you are going to put this a here, the real part of the imaginary number will lie in this axis, in the axis of the real numbers. So the b that you're going to have with this unit over here, with this I, meaning the imaginary, okay, with this I, is what we call the imaginary part of this imaginary number. Is that okay? Now, suppose here we have a certain value of a, okay, and here we have a certain value of b. Suppose this is b. So then you just plot this one. This will be here. Okay, so now the distance from the reference, okay, till this point over here, we call module of z. Okay, this is what we call module of z. So what is module of z? This is the distance between from here till there. So this is the module of z. And we know how to calculate this module over here. I will just show up there. So, and here we have an angle, the angle between this module of z and a, okay, we call argument for this imaginary number. Okay, that's all in a short view about this imaginary number. So any imaginary number, then from here we know that from here till here, I've got this triangle over here. This is a, and this distance from here till here is the same distance from here till here. So it means that here till here it is b, here till here it's b, that's fine. So then it will be our b, the complete interval from 0 to b, it's equal to b. From 0 to a, it's equal to a. Just like this. Okay. A and B. And here we know that that is Z, modulo Z. Here we have our argument. So whenever we see argument, it means that the angle between the real part, okay, between the distance, how can I say, between the module of this imaginary number and the adjacent side, that is the real part of this imaginary number. Okay, so how to find then what is theta, that is the argument of this z. So the argument of this z. So to find this guy, you can just plot many ways, many things. You can just come here. This argument can be found by sinus, cosinus, or tangent. It's up on you. But usually, it is made by this way, like argument. You just plot by tangent, like b by a. Okay, b by a. Nice. So this is tangent of b by a. This is what we call the argument of this z. Tangent inverse, okay? Because actually, if you find the tangent of theta will be b by a, then what is this? So theta will be tangent inverse of b by a. Nice. So now that we know this, so this is this. Now what is z? Okay, as we can see here, z will be the radius. Okay, the radius is the same as radius, or is the same as root, okay, of this a square plus b square. So this is what we call the radius. That's why we can write these imaginary numbers like z. We can write z will be equal to what? Suppose here I came here. If I come here, okay, just a point. So sorry, yeah, just if I come here, suppose I come just here, what will happen? I can write just this one. What I will do, I come here and I can put this module of z, okay, and I can just do this, a upon module of z plus I b upon module of z, okay, just like this. It will be the same because z is equal to what? Is equal to a plus ib. So if I put here module of z time module of z upon module of z, then upon my module of z, it will be the same, this expression over here. So I just, what I put, I took, okay, nothing changed. But the question is, why am I doing this? Okay, I'm trying to find the other form, the other form or the other way to write a an imaginary number. And what is this other form? Now see, here from 0, from the origin till here, we call this one, the distance from the origin till this point, till the point here, we call module of z. Okay, this module of z is the same as this, as the radio of this circumference. So I can call this one r, this one module of z is r. Okay, then what we have there, we have a upon module of z, b upon module of z. Now check here, what is a upon module of z? A upon module of z will be what? If we just find this one, let me just plot this. This is module of z, this is a, this is argument, this is b. A upon module of z, it will be cosines. Okay, it will be cosines. Let me just write it down. Means that I will get cosinus theta will be equal to a upon module of z, and sinus theta will be b upon module of z. Okay, just from here you can see directly. So it means that here we have cosinus theta plus I sinus theta. this is the other way and the most common way to write a uh, an imaginary number. Okay, yeah, this one. So I'll call this one star. Okay, this is also a way to write an imaginary number, but usually you'll find this is the first way. Then you'll find the second way. Then there is a third way. Okay, this third way is derived according to the Euler's equation. Okay, what is Euler's equation? It says that when I have Euler raised to I x, it's equal to cos theta plus I sinus. So it's not theta, actually it will be x. Okay, and here sinus x. Okay, this is the other way to write complex number, because if you just compare cos x cos theta, then I sinus x. Okay, this is Euler equation. So this way, by using this guy, then you can just come here z. Okay, what will be z? You know, here cos theta plus I sinus theta is the same. If you compare, this expression over here is the same as this. So we can just write here, put here your r, this is your r, keep it, then multiply by I theta. Okay, that's all. So because u raised to I theta will be what? Will be cos theta plus I sinus theta, as you have here by Euler equation. Okay, so these are the two ways to write your argument to write your complex number. The first one is by using general notation. Then you can plot this graphic over here, find the cosinus and sinus. Then you have just to put modulo of z and take modulo of z. We know modulo of z is the distance from here till here, so it will be the same. Okay, the same as the radio of this circumference. Then that's fine. Is that okay? That's fine. So now that you have the basic things about how can I say about this, so we are going just to show why the argument of z1 upon z2 is equal to the argument of z1 minus z2. And if you can see here, this r stands for radius. Okay, stand for this module of z. Okay, then theta here stands for nothing more than the argument of dz. Okay, the argument of dz. Now let's go. Okay, now the question is why, okay, why argument of z1 upon z2 is equal to argument of z1 minus argument of z2. Argument of z1 time z2 is equal to argument of z1 plus argument of z2. So for this, we are going to apply some, we are going just to prove, okay, one by one. Let us start from, okay, for the easiest one that I think. So suppose we have argument of z raised to n. Okay, what will be this? It says that argument of z raised to n is n argument of z. So the first thing you have to understand is that argument stands for theta. Okay, it's the angle directly. So how to find this? The first thing is, we know that z is equal to r cos theta plus I sinus theta. Okay, now that we know that this is true, so z raised to n, then I come here, I put the power n, and here to the power n. So when I got this, what will it be? It will be z raised to n, and here we'll get r raised to n, then I'll get cosinus theta plus I sinus theta raised to n. So the first thing I have to just see here is there is a very common and very known, okay, theorem that is Moivre's. Let me write here, Moivre's theorem. Okay, so by Moivre's theorem, we know that whenever we have like z raised to n like this, raised to n and cos theta plus I sinus theta raised to n, it is all of this. This is the same as r raised to n, and here cos of n theta plus I sinus of n theta. Okay, just like this. We know this. Okay, yeah, we know this by Moivre's theorem. Okay, but if you are confused about the Moivre's theorem, you can also say, okay, you know that z raised to n is the same as, we know that z is equal to r Euler raised to I theta. Right? We know this. Okay, this was the third form to represent a imaginary number. But if we know this, so if I come just here, raised to n and raised to n, so what will be your z? So z raised to n will be r raised to n, then Euler raised to I n theta. Then if you extend this, what is Euler raised to I n theta? It will be r raised to n, Euler raised to n theta. We know that Euler raised to I theta is cos theta plus I sinus theta. Okay? Now if we add n here, it means that here I will get also n, and here I get also n. So then I can write cos n theta plus I sinus n theta. Okay. So from here we can directly see, that what is the angle for z raised to n. Okay, when I have z raised to n, I know that the angle will be n times theta, n times the argument. So the question there up is, what is the argument of z raised to n? So the argument of z raised to n will be what? N argument of z. So we know that argument stands for what? Theta. So here I would also write n theta. Okay? Because that's the question. Here the question, they are just looking for what is the angle when I have z raised to n. So you come here, just solve this one, and you check whether you do by Moivre's theorem, or you can just come here by using the third form to represent a imaginary number. Then you can just directly make it happen by the Euler's theorem. Okay, just like this. Then it is said, what is the angle here? N times theta, n times argument. It means that when I have z raised to n, the argument of z raised to n will be n theta. As you can see here, argument of z raised to n is n argument of z, that is n theta. Right? So, okay. Now, let me go for the next one. Okay, just leave it. So, the next one is, what is argument of z1 times z2? what I have to do, I want to know. And they say that this is equal to the argument of Z1 plus argument of Z2. Right? So to write this, okay, to solve this equation or to prove this sentence, what you have to do, we have to write what is Z1 times Z2. Okay? And here we have two ways to demonstrate this. Okay? Whether we can solve by the, how can I say, applying Euler's equation, because we know Z1 is what? Z1 is Euler raised to I theta 1 and, okay, and Z2, let me just write here, sorry. Z1 we know, okay, by the third, you remember when I have Z is equal to R Euler raised to theta I theta. Okay, by this one you just apply this one I theta R, yeah. If you just apply it here for Z1 and Z2, what you're going to have, you're going to have R1 Euler raised to I theta 1 times R2 Euler raised to I theta 2. Okay, that's what you have. That's what you got. Right? Now, if we have this, what does it mean? It means that just you are going to have R1 times R2. Then this one are what? These are powers. Power is the same. Power. This one power. Okay, and they have the same exponent. So I can just keep the power, then sum the exponent. It will be I. Then here I'll get theta 1 plus theta 2. Is that okay? Now that it is like this, so what will be this? What will be this? Okay, by Euler's, okay, by Euler's theorem, Euler's equation, sorry. Euler's equation, sorry. Yes. By Euler's equation. Okay, sorry for my graphy. Okay, but Euler's equation, what you're going to have R1, R2, and this will be cos of theta 1 plus theta 2 plus sinus of theta 1 plus theta 2. So what you can say about this? So you can say just that what is the argument of Z1 plus Z2? What we mean by this? We mean what is the angle? Okay, when I multiply Z1 and Z2, what is the angle? The angle is this over here. So it is proved that argument of Z1 times Z2 will be equal to argument of Z1 plus argument of Z2. And that is what you got here. It will be theta 1 plus theta 2. Done? Fine. Now, let's jump for, suppose it is division. Suppose it is division. Just come here. Okay, no problem. I will just show up. Division. Suppose we have here division. Okay. Okay. So what we have here a division, like what is argument of Z1 divided by Z2. Okay? Yeah. They say this is argument of Z1 minus argument of Z2. That's what I say. Okay? So, yeah. And there is another, how can I say, another something about argument that I would like to explain also. Maybe I will just prove. Argument, suppose, of Z, of the conjugate of this Z. Conjugate of Z. What will be this? Okay, so I will then after solve this. But argument of Z1 minus the argument of Z2. how to prove? So we know that make just Z1 upon Z2. It will be R1 and here R2. Euler raised to I theta 1, then Euler raised to I theta 2. Okay, so now R1 upon R2, then Euler, just keep constant the base, then subtract the exponent. Then what you're going to have I theta 1 minus theta 2. Okay, now apply for this expression here, apply what? Apply Euler's equation. So what you're going to have R1 upon R2, then cos of theta 1 minus theta 2 plus I sinus of theta 1 minus theta 2. Then it's proved. So here we can say the argument of Z1 upon Z2 will be this, theta 1 minus theta 2. This is this. Then it is proved. That's fine. Okay? So again, what will be now argument of what is argument of the conjugated theta, this negative conjugated this one. Okay, how to find this? Okay, they said that argument of this one, argument of the conjugate this one is equal to minus argument of z. Now let us prove, let us see whether this is okay or not, this is false or true. Okay, so we are going to have argument of z, it's equal to, sorry, not argument actually. Then we are going to have, what is z? Okay, z conjugated. Suppose we have, okay, let me write, here it is a, sorry, it is z, r, let me call z r raised to I theta. Okay, so what would be z conjugated of z? Okay, we know that z can be written as this, or z can be written as also like this, r cos theta plus I sinus theta, or z can be written also like this, a plus ib. So what is the conjugated of this expression, of this expression, of this expression? So if you find the conjugated of this, what is the conjugated actually? The conjugated is the term that will make this guy square. Okay, whenever we are seeing conjugated, how can I say this one? Suppose we have this one like a plus b. What will be the conjugated of this expression for a plus b? The conjugated will be the same expression, like I will keep the same a and b. What will I just change? The conjugated expression will be the, how can I say, the same expression a and b, but it will be just symmetric in the sign. So this one. Okay, so what will it be? It be a square minus b square. So then I will call this the conjugated of this one. So the same will happen here. If I want to find the conjugated of this expression, so the conjugated of this z, for this z, it will be what? It will be r cosinus of theta minus, instead of plus, I sinus theta. Okay, and the same will happen here, z. Okay, because the conjugated is the inverse actually. Okay. Okay, the inverse function. So what is this? What will be this? Will be a minus ib. Okay, this will be the conjugated for this one. This will be the conjugated for this one. And what about for this one? The conjugated for this z is nothing but r Euler raised to minus I theta. Okay, so either if you go this way, that way, or any of this way, you are going to end with the same conjugated. And I'm just proving, applying Euler's equation, because it is the easiest way to do this one. Okay, you can also apply some trigonometric function and this kind of thing. you get the same solution. Okay? Nice. So, let me prove then. Okay? What will it be? So, it will be, okay, so it means that the argument, first, if I have z, z is r Euler raised theta I. Now, what is the argument of z? So, what is this one, the conjugated z? The conjugated z is r Euler raised to minus theta I, or minus I theta. It's okay. Now see, what will it be? It will be r, what is this Euler raised to minus I theta? Okay, it is cos of minus theta plus I sinus of minus theta. Is that okay? Nice, that's fine. Now, how to do this? What or how will it be? How will it stay just the point? So see, here I have minus, right? So, sorry, what will it be? So, when I get cosinus of minus theta, we know that cosinus is a even function. It means, what we mean by even function, we know, okay, even function is the function that is symmetric, okay? Suppose, let me just, it is symmetric with respect to what we call this, for cosinus function. Let me just draw the cosinus function. We start from here, okay? Then it go here, it come here, and then okay. So, an even function, or an odd, an even function is a function that is symmetric. It means this side will have the same measurement to this one. Okay? So, when a function is symmetric inside, like this side is equal to this one, okay? And this side, if we join all the parts of this side, will be equal to all the part of this side. The only difference will be in the signal. Okay, so whenever a function is symmetric with respect to y-axis, so we call this function a even function. Okay, and the algebraic way to demonstrate this even function is by this expression here. F of minus x is equal to f of x. Okay, so whatever function that can accept this condition is called as a even function. This is algebraically representation, but graphically and by definition, this is the right way to define an even function. Now see, f of minus x is equal to f of x. So what do you mean by this? F of minus x, okay? So just come here. It means if I put minus cos of minus, whatever the angle, is equal to cos of theta. Okay, then just try in your calculator. You will see that cos of any negative angle will be the same as cos of whatever positive angle. So, but for sinus, it will be the opposite, because sinus it starts from 0, start from here, then go up, then it go up, and then so on. See, sinus is symmetric, or it is like a symmetric with respect to, how can I say, with respect to this point over here, to the origin. Whatever graphic of any function, if you want to see graphically, or if you want to define an odd function, are those functions that are symmetric with respect to the origin. Sinus is symmetric with respect to origin. If you draw the sine, like what is the name? The graphic of sine, it will start from here, it will go from here and here. This part over here is exactly the same as this. Okay? But here, your mirror is not the y-axis. Here, your mirror is this origin over here. So, if they are similar, okay, if this area is the same as this area with respect to y-axis, so this function is called an odd function. So, algebraically, an odd function is that function that accepts this condition. Okay? f of minus x is equal to minus f of x. That's why here we can write r cos theta minus I sinus theta. Okay, we can write like this. Okay, we can write like this. So now, what we mean by that? Okay, I was just explaining about this odd and even function, but the point here is not about odd, neither even function. The point here is only one. See, analyze. If you analyze well, you will notice that you will notice that the argument of z here is what? Is minus theta. Argument of z is theta, but the argument of what is the name of this? Of the conjugate of z, the conjugated term of z will be minus theta. This one, this is the conjugated for, this is the argument for the conjugated, okay, the conjugated term of this z. So whenever we have z conjugated, okay, the conjugated term of z, okay, his argument will be always minus theta, negative, as you can see here, negative. But here I just solved, okay, just to find out just to show you that this guy here, okay, is the same as this guy and is the same as the conjugated negative, where if you can see like this, just like this. Here you can see that this is a plus minus ib. This can be written like this. As you see, this one is z dash, this one is z dash, and this one is z dash. What is the argument for this z dash? Minus theta, when he is z dash, as you can see like this. Okay? Okay, so I hope you may enjoy this. Welcome to India. You see me, I'm sweating. It's not because of maybe internal pressure or something like this. It's because it's India, and here it's a little bit hot. Not a little bit, it's hot. Okay, so if I do not switch on the fan or something like this, that will be the nature of the videos. But thank you for staying with us. Okay, all the best, and see you when I see you. Bye.